Okay, so I would like to thank the organizers very much for inviting me to come here. I'm a co-organizer, but I did not invite me. I know that. It's very difficult to give a talk like this because I know that I have so very good speakers in front of me and behind me, and I know that there are many people in the audience who are not really specialists in the field. The message in my talk basically is a message, and I will repeat it in the end of my talk, which has happened in physics and in science many times. And that is that some of the really interesting developments come about not because people wanted to build something, but because people were curious and they wanted to know something new. But before I go into this kind of thing, here is a picture which confirms in part something else to which Schrödinger contributed, Schrödinger equation or whatsoever. That is a very old picture which we took a long time ago in 1988. It's the two-slit diffraction experiment or double-slit diffraction experiment with very cold neutrons. Why do I show you that? Because for various reasons. One is, at that time, and still today, I think in terms of absolute intensity, it is difficult to match the precision because the solid line here is just standard Schrödinger equation with no free parameters. The only free parameter is the total intensity. So all the features come in by precise knowledge of the setup. Second point, and this has implications, namely it has implications in the sense of setting limits to alternative variants of quantum mechanics, which I understand have not been surpassed by atomic or whatever experiments so far for a reason. The reason is that the neutron does not like to interact with the environment. So it is in itself, it is very well shielded. Second point I want to make is the intensities here are single particles intensities. And this is true for all the neutron experiments, which, as you know, were pioneered here by Helmut Rauch and his people here in Vienna. It is true that for all these experiments that when you detect one neutron, the next neutron, which you will detect, is still sitting in the uranium nucleus waiting for fission to happen. So it's really, in a sense, most of the time the apparatus is empty and sometimes there's a neutron. And we collect those neutrons and we get the wave pattern. Now the simple fact, and this is the third point I want to make now, the simple fact that the neutrons distribute according to this pattern, and if this were an experiment where we had, for example, exactly monochromatic neutrons, then the minima would actually go down to zero, which has been done for photons, by the way, with very high precision. This fact that there are points where each particle knows that it should not go to indicates, and I quote Feynman here, that the wave function describes individual particles. Otherwise, it is not just a statistical phenomenon. Okay? And the fourth point I want to make here is the following. This about the kind of a joke about the role of the observer in quantum mechanics. When we did this experiment, we actually did some other work. We had a beam at the reactor in Grenoble at that time, and we wanted to go skiing, but we had 10 days left to do a measurement. So which experiment to do where you can go skiing and which runs on its own? So we did this experiment. And we came back after 10 days, and the pattern was there. And the only person who maybe observed occasionally the experiment was the janitor. That may tell you something about the role of observer in quantum mechanics. But this is just for the fun of it. And finally, here is this kind of experiments allows to put limits on nonlinear variants of quantum mechanics. And here's a beautiful form of a nonlinear variant of the Schrödinger equation. I don't know how Professor Fröhlich would fit it into his scheme of different theories. This was invented by Bialinitsky, Birula, and Mizielski Bielski-Birol is a very famous theoretical physicist from Poland. And what he said is if we add a term to the Schrödinger equation, which is a function of psi squared, and more precisely, if that term depends on the logarithm of psi squared, then we can achieve two things. We can achieve, firstly, that wave packets do not spread beyond any limit, but this is kind of a self-potential. So this would make quantum mechanics a little bit more palatable, maybe. And secondly, if the logarithm is, if there's a logarithm, then you have you can, because of the nature of the logarithm, you can separate the Schrödinger equation if you have non-interacting subsystems into separate equations, which is a very reasonable thing. So in the experiment, we were able to put a very low limit on this kind of thing, which was so low that Bielski-Birol did declare defeat at that time, which was quite nice. I want to mention just research going on here, because this is not part of any talk at this meeting because of time limitations. This is a series of experiments going on where I participated in the beginning, and now it's done by our chairman, Markus Arndt, with his own beautiful line of research. This is a pattern of essentially the double slit. It's actually, I think, 2.5 slits on the average, which I illuminated coherently. With Fullerenes, done a long time ago. The point I want to make here is that the solid line here is a linear Schrödinger equation in a Fraunhofer model, and in order to get the real pattern, you have to include the Casimir interaction or however you call it. There's a long line of research, and this connects to Schrödinger again. There's a long line of research going on to see quantum phenomena of macroscopic systems. There's the continuation of these molecule interference experiments. I understand that you are now at mass numbers of about 7,000. Is that nearly 8,000? Okay, so it's going on. Then there's another line of research where I also participated in the beginning, but this is now done by Markus Aspelmeier on his own, and there's a big emerging field worldwide. While interestingly, here in Vienna, we are still the only ones. There was one group who had attempted, but they gave up. This is a big line of research to see quantum phenomena of micromechanical systems. We are still far away from realizing Schrödinger's cat. Here you have Schrödinger's cat paradox, which is often discussed as a question of but you can see superpositions of live and dead cats. I would rather suggest it's a question to see entanglement of different cat systems with macroscopic apparatus, with other apparatus like the poison and so on and so on. There are scores of papers where you can see where people argue why we will never see a Schrödinger cat in this kind of superposition. I mean, the superposition between life and dead is something a little bit artificial, maybe, and one should not. By the way, the experiment has not been done yet by anybody. There are lots of papers why this will never be seen in experiment. The way I, as an experimentalist, read these papers is that I say, yes, they are all correct, but maybe there's a way to go around. Maybe there's a clever, and I actually can make some suggestions how to see quantum superpositions of living systems. You just have to make sure that you handle the coupling to the environment in the right way. Now, but we are very far away from where our friends across the pond in the United States are. This is a parking lot near Washington, D.C., and I get this picture from Charlie Bennett. It clearly confirms that they have already quantum cars, which can leave parking structure in a coherent way. And the confirmation that they are there is that the quantum cars exist is because you don't see them here. Observation would reduce the wave packet. Now, to come back to one point, which I think everybody of us knows, and I don't tell you something new, but I want to stress this because there is often a big discussion of where is the boundary of classical phenomena. I think the right way to say is that there is no boundary. This goes already back to explicitly the first person who said this in my eyes was Bohr in his discussions with Albert Einstein. There is no boundary, and it depends on you as an experimentalist whether a given system behaves quantum mechanically or classically. It is your choice of apparatus which determines whether the system is quantum mechanical. So there is no objectivity to being quantum or not. Now to come to entanglement, you have seen this first line already in Brigitta's talk. It was hidden in one of her transparencies with many other information. So I put it up again. This is a paper which came out in 1935. And I would like to stress again, I mean, some of you have heard me talk about this before, but not everybody, so I repeat it. This paper was published by a physical review without ever having been seen by a referee. They actually did not usually send referees out then. For example, Einer in der Physik, which was edited by Max Planck because he was the permanent secretary of the Mathematische naturwissenschaftliche Klasse of the Prussian Academy of Sciences, he himself has decided whether to accept the paper or not. No referee involved and so on. Okay, that's the way how to do it. And actually, in the old days, the way it worked is he decided within a day or two. Then they set the paper in print within a week, and when it was urgent, he sent a courier, a person, to the author, asked the author to correct it right away and had it back. So within 2 weeks, the paper was published. Tell me a journal where this happens today with all the electronics and so on. But never mind. So here Albert Einstein introduces the notion of entanglement, the fact that you can have quantum states which are states of multi-particle systems, but which cannot be factored into individual into product states. Now see, I have no idea why this comes up. So my computer does something. Here we go. Okay. So here's something which tells you, in a nutshell, the development of the field. And that's the reason I show it. This is actually the title of my talk, in a sense. Here you see the quotations of the EPR paper. The quotations of the EPR paper, the paper was published in 1935. And there were a few quotations in the beginning, and then it was dead. And it starts slowly again, and there are two surgencies. One is in the 1960s, there was the paper by John Bell published, that the viewpoint exposed in the EPR paper is in contrast to what is called the philosophical position of local realism. And then a little bit work came up, then experiments came, and there's an explosion. There's an explosion in the late 90s. And this is when it turned out that entanglement can be useful in quantum information science. And now the paper is quoted, as you see, 200 times a year, so every other day, which I like to stress does not mean that it is read more often than in the old days. People just quote it. In the same year, it was already mentioned, Erwin Schrödinger published this paper here, Die gegenwärtige Situation in der Quantenmechanik. This was actually 3 papers because the paper was too long to be published in one. It was 3 subsequent issues. And this, for every one of you who have not read it yet, read it. This is a fantastic paper. Here's the content of some of the thing. He talks about Verschränkung already in the title, in the content. He coins the term Verschränkung, as you have heard, and the notion entanglement was coined by him in the same year in a paper published by the Cambridge Philosophical Society. When he discusses about Verschränkung, he uses some very modern notions. He says that Verschränkung is a situation where maximal or complete knowledge of the expectation catalog, he calls it. I would call it today, we would call it information. Maximal knowledge of the expectation catalog of the joint measurements of the composite system does not only not imply a knowledge of the individual catalogs, but also actually precludes it. So you can have a situation where you know everything about correlation, but where nothing about the individuals is defined in any way in the experiment, in the situation itself. In modern language, information is encoded in joint measurements and not in individuals. The question is, besides formal argument, what is the reason for this? I mentioned at some point, but I don't want to go into this now, that I believe that it is because of the finite information which a quantum system can represent. Here's again Schrödinger with the notion of entanglement. So we talk about an entangled system, in this case 2 dice, and the point is that you have a complete expectation catalog for the joint measurements. That means perfect correlations, but no expectation catalog for the individual measurements. So these are completely random. It's actually interesting to note that Schrödinger, while he coined the notion of entanglement and so on, in my eyes, did not pursue this issue later on in his life. I would be interested to know whether he did something more. Actually, somebody told me, I should dig that out again. Erwin Schrödinger wrote very briefly after the EPR paper, he wrote his paper where he gives this very careful analysis of entanglement. And I always was surprised why he could do it so fast. And somebody told me that he actually had been working on the problem for a couple of years. So it was, in a sense, in the air. It was an interesting, probably formally speaking, if I'm not mistaken, the first time entanglement came up, but our mathematical physics friends probably know that better, was done when Pauli solved the helium atom. But there it is implicitly there. It should actually be there already for the hydrogen atom because of the entanglement of the motion between the nucleus, because they move around the center of gravity. I don't know whether this has been explicitly written down. Would be interesting. But anyway, and here's the citations of that Schrödinger paper over the years. You see the number of citations is lower, even now, probably because it's written in German and not in English. But the citations take up much later than for the EPR paper. So it took people obviously some time to realize. Now you have seen this kind of thing already implicitly in Brigitta's talk. In a nutshell, the situation for entanglement between two photons which might be both horizontally and both vertically polarized. This is a superposition state. It cannot be factored into separate states, and it prescribes that you have perfect correlation, and therefore following Einstein, Podolsky, Rosen, one might assume that one can introduce what they call the elements of reality for the individual measurement results. And then Bell showed that if these elements of reality are local, under his definition, then they are in conflict with quantum mechanics for statistical predictions of the theory. The measurement, the quantum expression is the Bell's inequality, which is a sum of certain expectation values. The important point is, intuitively, correlations between measurements in quantum systems can be stronger than classical correlations. Okay, I will mention a recent thing about that very soon. Here's a way how to produce such an entangled system. A source which we developed with Paul Kwiat when he was a postdoc with me many years ago. We pump a nonlinear crystal. We create pairs of photons, feed them into two glass fibers, and can play with them. Now here are what is now called the Bell states, the 4 maximally entangled states between two photons. And here I would remark something important, and that is 3 of these states are symmetric upon exchange of the two photons. One of the state, namely psi minus here, is antisymmetric, so it changes its sign. This is only possible, clearly, if the spatial state of the photons is also antisymmetric. And I saw in your talk, I saw the state of 2 electrons, which was antisymmetric. It should be possible there to have a symmetric spin state if I create in the experiment a situation where an antisymmetric spatial state. I don't know if that has been done by already. I don't know, to have two electrons in a symmetric state. That would be the counterpart of the... in any case, in our case, this fact that here you have a minus here is very important in many of our experiments. Now, there's a long history of experiments confirming to a better and better precision the predictions of these correlations, and ruling more and more out a local realistic viewpoint. I will say more about this. This was an experiment which we did many years ago in Innsbruck, but this is historic. I don't want to go into this kind of details anymore. There are a couple of loopholes in the experiment, and I'm sure that people will actually discover new loopholes. This will happen, I think. In this kind of experiment, we ruled out what is called the communication loophole by rapidly switching the polarizations on 2 sides. To remark, again, a connection to quantum information, and I don't know if he's in the audience, Danny Grimberger. Is he here? Huh? Here he is. Back there he is, yeah? Very good. Okay. About 24 years ago, Danny Grimberger visited me in Vienna, and when he came, on the first day we sat down, what should we work on? Basically, we wanted to work on entanglement, and we realized that nobody had worked on entanglement of more than 2 particles so far. So, and we were both interested in it, you see, and what we did not know at that point clearly was 2 things. Firstly, that for the measurements between 3 entangled particles, you have much more violent contradictions between local realism and quantum mechanics. And secondly, that these states might be useful for some information processing, which is the case today. I don't want to go into details here. Today, these states have a physics abstract classification code entry, as I've discovered. Here's an experiment which we did a couple of years later, mainly Gian Pan and Dick Baumeister in my group and Harald Weinfurter. The basic point is that you look at correlations between 3 measurements and 3 photons, horizontal and vertical polarization. A local realist would expect this kind of, a quantum mechanic would expect this kind of correlations. A local realist would predict these, and the quantum mechanics in the experiment, we see this. The point is that the local realist and the quantum mechanic make completely different predictions for one single measurement once you know 2 measurement results. Here, I invented a little example, but let's go on here. Let's go on from here. Now to the applications in quantum information. There are various applications. One is quantum cryptography or quantum key distribution. I should mention that there are basically two different schemes in quantum key distribution. One uses, in the ideal case, single photons, going back to Bennett and Brazard, and the other one uses entangled photons. The world expert in breaking the single photon case is sitting here in the front row, and here he is. Right. But as far as I know, and he also broke some entanglement-based systems, but we want to ask him to break our systems in the future. Now, the point is that you have Alice and Bob connected by some classic channel, and by this was the idea of Andreas Poppe, who did this kind of thing. And you can have them, the ideal case, you can have the two connected with the classical channel and quantum channel, and an eavesdropper can tamper with both channels and still, in principle, not get at the information. The entanglement-based system was proposed by Arthur Eckert, and to the best of my knowledge, this is the first proposal where entanglement was used in an information processing suggested in an information processing context. The basic idea simply is that you use the perfect correlation. This is a picture of our experiment done sometimes later. There were 3 experiments published in the same issue of Physical Review Letters, realizing this kind of thing. You use the perfect correlations to establish a key for communication between Alice and Bob. This was done in 1999, but the first realized proposal was dense coding, super dense coding by Bennett and Wiesner, proposed by Bennett and Wiesner in 1992, just 1 year after Eckert. And this was the experiment which we did first in 1996 because it was easier. I should mention one point, and that is historically maybe of interest, I don't know. Ever since Danny Greenberger has worked with us on these 3-particle correlations, I wanted to do that experiment. And that took us about 10 years. And along the road, we developed tools which we could use for all these other experiments, like cryptography, like dense coding, like teleportation, and now quantum computing, and so on and so on. So these are just spin-offs of the main goal, which was the 3-particle correlations. Now, in dense coding, which is actually a very nice idea, the point is that you have a source which creates entangled particles, and Bob has access to only one of the 2 particles. But by having access to only one of the 2 particles, he can navigate around in a 4-dimensional Hilbert space. If these are the 4 maximal entangled Bell states, by just playing around with lambda over 2 plates, he can switch between horizontal or vertical polarization, and he can change the phase here. So he can encode, by modifying only one photon, here he can encode 4 different messages, that is 2 bits of information, into his photon, which would not be possible classically. All Alice has to do is she has to identify which of the states behind you have. As I mentioned, as far as I know, this was the first realization of an entanglement-based quantum information scheme. Another idea is teleportation. I don't want to go into details here. You teleport a quantum state here using entanglement as the bus to transfer quantum state from A to B. The idea was Bennett, Bazar, Crépeau, Joseph, Perez, and Wouters. Here's our experiment many years later. But I should mention one point which is interesting, which is this fermionic nature or antisymmetric nature of the quantum state. Sometimes, here's the situation, if our state is antisymmetric for 2 photons, if it is antisymmetric, for example, in polarization, if this is horizontal, vertical, horizontal, then the state is also antisymmetric in the external mode, in the space. And the propagation at the beam splitter, if you have a 50-50 beam splitter, the behavior, each photon has a 50-50 chance to be reflected or go through. The behavior at the beam splitter is determined by the spatial part of the state. So if the spatial part is antisymmetric, then the 2 photons behave as if they were fermions. So they go on. So if they go in separate channels, they always go out in separate channels. They do not bunch. And that was a very important discovery we made in 1995, because that way, this is the only state which behaves that way. And basically, when you see anti-bunching of photons on a beam splitter, you definitely know that you have projected them onto an entangled state. This is the only possibility to have anti-bunching. And that is a very important experimental signature. And I would feel for electrons, the reverse should be true. If you detect 2 electrons in a bunch state, then they must be entangled. But maybe one should talk more. I don't know. Okay. Here one futuristic application which has not been not been realized yet. I like to put it up, even as this is also an old idea. I'm running out of time by just talking about old ideas, so I have to speed up. This is a scheme which we invented many years ago. The situation is the following, that you can be using a quantum computer and quantum teleportation. You can beat any classical computer because in principle you can teleport the input, which is the input of your computer. You can teleport the input back into the past. So you can start the quantum computer in the past with the input of your calculation, and the input can be ready even before the output can be ready even before you have the input. This is quite interesting. There are no paradoxes, I promise you. There's no paradox because the scheme is probabilistic, which means that it does not always work. But when it works, you know that it works. That's important. When it works, you know that it works, and then you can use it. So, for example, if you go on Wall Street, sometimes you have the right prediction, and you can immediately play with it, and you know when it's the right one. So it's quite interesting. I don't want to go into details here. Here's a conceptually interesting question, and that is they use entanglement swapping, which is simply the teleportation of an entangled state. So you have two pairs, and you teleport, for example, this state over there or this state over there by entangling these two. This is an essential feature of quantum repeaters now, where you also have small quantum processes here. But the important point is that you entangle photons which have no common past, or particles whatever which have no common past, which is conceptually interesting. And it has been pointed out by Asha Perez, it was a nice proposal by him in 2001. You could actually have the following, that you register these two photons before, at some time, and at a later time, you decide whether you project these on an entangled state or not. So at a later time, you can decide whether the two photons which have already been entangled, have already been registered, have been entangled or not. This is quite interesting. And how can it, this is not a contradiction, it's quite interesting, but it tells us something very deep conceptually, namely that the events, the primary events which we register, they just happen in a sense. They don't care about our interpretation, whether we interpret them as entanglement or not or whatsoever. The song and dance we make up afterwards is a different story. Now, we have done such an experiment recently. It was done by Shasong Ma in my group, and we are writing the paper up now very soon, I hope. But okay, he's laughing. Yeah, he knows why. No, it's my fault. So now to come back to the fundamental issues in the last few minutes of my talk. There are at least three loopholes in these Bell experiments. One is called the communication loophole, namely that when you test local realism with a static experiment, it could in principle be that one photon or one apparatus communicates with the other one when they arrive within each other's light cones and so on at the mutual rapport what to do. I mean, this is a crazy idea, but if you want to test a theory fundamentally, you have to test against that. And the first experiment in that direction was done by I should mention that here, by Aspect, Grangier and colleagues in the 1980s by using periodic switches. We did an experiment in 98 with random switches. Then another loophole is a fair sampling loophole, namely that if you don't detect all photon pairs, then it could very well be that the total sample violates quantum mechanics. Only the subsample which you measure obeys quantum mechanics. This has been first mentioned, if I remember correctly, by Pearl a long time ago. It was closed for photons. You have to detect at least 2/3 of all pairs to close this loophole. That can be proven. It was closed by the Vineland group for two atoms or two ions sitting in a trap, but very close to each other. So they had ample time to communicate with each other. What is missing is an experiment which closes all this. And there's a freedom of choice loophole, which was already defined by John Bell, but has not been discussed, interestingly, in the community very much. I don't know why. It's the assumption that the choice made by the two pieces of apparatus must be free, must be independent, must not be influenced by a common cause. Now the big question is how to close such a common how to exclude such a common cause, because in principle anything could happen. Well, one can exclude reasonable subsets of that assumption, and one which we did recently was to exclude that the influence which might choose the measurement apparatus is created together with the particle pairs, and this can be done by having the choices space-like separated from the source. And one could ask another question, and in the early days, it was actually, I don't know who it was, but it was on the first meeting in 1976 where I had happened to participate on Bell's inequalities, and where I did not understand a single word. But I remember they discussed one possibility that one could use the light from two distant quasars, because they are the most independent sources of light from early days of the universe. And we might actually do such an experiment in the near future. So the experiment which we did was between La Palma and Tenerife. You have probably read about this. The reason to be there is not the reason you think we are there, but it's the reason that there is the European Northern Observatory here. There are clusters of telescopes, and there's only one other location on Earth where you have these conditions even a little bit better, and this is on Hawaii. Between two islands on Hawaii, you actually have a little bit better conditions. Again, not because of the reasons you think, but because the telescopes are much higher up there. They're at about 4,500 meters, and here we are at about 2,500 meters. So we have a quantum link, and what we do is we create our pair of photons, and we assume that the hidden parameters, or however you call it, are created at the source, which might influence the future. So what we do is we send one photon over to Tenerife. This line is wrong, it should be here, and that I don't know how to fix that. And the other photon is kept locally. You don't have to send it away, you just have to make sure that its decisions when you do measurements have to be space-like separated. So this is the future light come from the source. So for Tenerife, it's easy. You do the decision sometime a little bit earlier, what to measure a little bit earlier than the measurement itself. For the other location, which is on the island of La Palma, you do the measurement outside the light cone at a few kilometers distant, at the same time nearly as when the two pairs are emitted. So again, there's no information possible going from here to either there, or vice versa. There's also no information possible if this is a really random process that these choices might influence the source to emit whatever would be necessary. The experiment was a big tour de force. Here are the two islands. On Tenerife, we have a source which creates these pairs of entangled photons. By the way, I should mention that this technology has received a very mature state. In the early days with Paul Kwiat, we had count rates of the order of maybe 50 per second. Now we have count rates of the order of more than 1 million per second. And the problem is to have detectors which are fast enough. And with very high purity. These are the purest quantum states one can produce. And what you have here is you create the two photons, you send one photon, one of the two photons you keep locally in a glass fiber and measure it at some later time. The other photon is sent over to Tenerife. And you create your random numbers by using beam splitters and using the quantum noise of the measurement after the beam splitter. And in the case of La Palma, this is generated at a distance of 1.2 kilometers, and the electronic has to be fast enough such that the creation event here and the creation event here can be space-like separated, and the photon still arrives in time to trigger the polarization measurement, to the choice of the polarization. On the other side, the whole thing is much easier because of the large distance. Here's the results, the tomography of the quantum state. This is details. Here's the results of the Bell state, 2.37. The classical limit is 2. So here are the people on the experiment. This was the thesis of Thomas Scheidel. Rupert Ursin sits here in the first row, who handles all the Tenerife experiments. He's the good spirit there. And I have to tell you, if you ever come to Tenerife and we are there, visit us. It's a unique atmosphere. It's really fantastic. Okay, I should mention now what remains to be done. What certainly remains to be done is a fully loophole-free experiment. An experiment where we close all loopholes in one experiment. This is open. For photons, this is open. It is possible to do it. In principle, if you put all technical possibilities really to the edge, it can be done. There are a couple of groups working on this worldwide. It is a race going on, and we will see who wins the race. It will be quite interesting. Now, I want to come back to some of the fundamental questions. There is the word Kochen-Specker paradox was already mentioned in Professor Fröhlich's talk. The question is whether the Kochen-Specker paradox is subject, whether it makes sense to do an experimental test or not. There are people who believe that it is just a mathematical statement and it's silly to test a mathematical statement. Well, I don't know. I'm an experimentalist, so we did the experiment. So consider the following game. This was invented by Radek Lapkiewicz, who did the experiment. Suppose you have these five locations, five places, which you can cover with cups, and you are allowed to put a ball under each of the cups or not. Okay? And the challenge is to make, and somebody is then lifting up two of these cups which are connected by a line. Two of the cups which are connected by a line. Okay? And your task is to distribute as many balls as possible in such a way that you have as many lines where you have one ball and no ball. One ball and no ball. Now the situation clearly is if here's a ball, if here's a ball, then it would be good to have no ball here and have a ball here, maybe have no ball here, whatsoever. If you go through, you must have a situation where you have at least in one case a ball on two neighboring lines. So you can have at most four connections where you have different balls. Not so in quantum mechanics. It was shown by Kliashko and these people here in the Physical Review Letters in 2008. If these five measurements correspond to five measurements on a spin 1, okay, five measurements on a spin 1 particle, then these five measurements can be shown to be equivalent to measurements of the square of a spin component, and that is the connection to Kochen and Specker. And you can, and if the quantum state is the measurement along the center of this pentagon, then you can have a situation where these correlations here are not limited to 4, but higher. So it turns out that if you calculate by quantifying this expectation value of two measurements, A1, A2, A3, and so on, where you can call one measurement result 1 if the ball is there, -1 if the ball is not there, and so on, then it turns out that quantum mechanically minus 3.94 is possible, while classically one is restricted to 3. So one can extend this inequality by adding the uncertainty between the first measurement and the repeat of the first, but these are details. Well, what it boils down to is that if you can explain, if you assume that you can explain the results by a joint probability distribution of the observables, a joint probability distribution of the observables, which you might not know, then this number k, which corresponds to the number of connections which can have different colors, can be at most 4. Quantum mechanics, it can be 4.94, which is amazing. It can be nearly 5 quantum mechanically, which is quite interesting if you choose the right state. And in the experiment, we find minus 4.81. So this is a test against hidden joint probability distributions, which might be seen as distributions of some realistic features to explain results on a single quantum system, not on correlated systems. So here's the team of the people who did the experiment. Radek was the main experimentalist who did whose PhD thesis. This is Sven is the postdoc, who is not yet a postdoc. He's still writing a thesis on the experiment, and Marcin was our main theoretical friend here. I don't want to go into this kind of thing. What does all this tell us? Together with the experiments ruling out the Leggett inequality, I subscribe to the interpretation of Leggett that this incompatibility of quantum results with classical or reasonable concepts has little to do with locality, but much more to do with objectivity. So, or in other words, with the idea that what we observe is an idea which is realistic. And this, I think, connects again to the talk of Professor Fröhlich. What needs to be done, and now we have to ask ourselves, what can be done? We have had various experimental situations where we test different combinations of assumptions. There are many fundamental assumptions still hidden in all these experiments, and we should find new situations testing other combinations of the fundamental assumptions. The fundamental assumption, like locality, then one assumption could be total determinism. All these problems would not arrive if the world were totally deterministic, including your choice as an experimentalist what to do. I find this in principle, untenable position, because it would mean that doing experiments makes no sense at all. There must be an argument that this kind of position is not tenable. You can assume that there could be actions into the past. You can ask whether the basic logic we use can be applied, and so on. There are many positions one can accept, and I think we need a broader view to this kind of thing. The question I like to ask is, why do we not have a test theory of quantum mechanics? By that I mean things like in general relativity theory, they talk about parametric post-Newtonian formalism with 10 parameters which you can play, and one of them is actually existing in nature. Why don't we have this in quantum mechanics? I pointed out before this one nonlinear modification. It turns out that if you modify the Schrödinger equation, or if you modify quantum mechanics, usually all hell breaks loose. So the formalism is so strong that there doesn't seem to be an alternative. And what I would like to have is either that somebody constructs a test theory of quantum mechanics, where we then can go and test various parameters, or somebody tells us why this is really fundamentally impossible. That this is the only way to describe nature for various fundamental reasons. I would like to know that. Would be interesting. Now, to come back to experiments, I believe that one of the futures is in space. We, again, mainly with Rupert Ursin, are planning to do space experiments, and it will certainly be an international collaboration. The only question is who will collaborate with us. This is now a very interesting political discussion. Just to show you the progress, we have been doing a lot of feasibility studies, and we are actually helping in the development of space-proofed equipment here. There is a lot of development. This is a graph of the first experiment done by John Clauser. The polarizers were Brewster plates, and here is the coincidence measurement. This is the graph of the same system, this quantum source, for a space experiment with all kinds of additional features and so on. I just want to improve. So I'm running out of time, I suppose, right, Professor?
Still a bit okay. We started late.
Chairman. Now I want to mention a little bit about quantum computation, but not much, because Peter Zoller will give the talk tomorrow, the last talk actually, and he's much more an expert in quantum computation than I am. Again, entanglement plays a role there. I want to point out one specific case where entanglement plays a role, and that is the case of what's called one-way quantum computation. In standard quantum computation, the paradigm is that you have a quantum system which represents unitary evolution, and the program is the unitary evolution of that quantum system. And you have an input, which can be a superposition or not, it doesn't matter. And the output is in general some superposition, and in general something entangled and whatsoever. And there's a big problem then because of the probabilistic nature of the measurement in the end and so on. But let's leave that aside. And I've been asking for many years, why does everybody talk about unitarity here? And people say, well, this is the only way how to do computation. Well, it's not right. I didn't have the idea. The great idea came from Miller, Flamm, and Milburn, and by Rausendorf and Brigel, that if you have a sufficiently complicated entangled state called a cluster state, or variants thereof, cluster states are highly entangled states which are such that if you take one particle out, the rest still remains fairly entangled, and they can be produced by nearest neighbor interactions. Now, if you have such a cluster state, then you can have quantum computation by progressing through measurements step by step here, step by step. So you measure one qubit, you measure which projects the rest onto a new entangled state, then and so on and so on. And the basic idea for this measurement-based quantum computation was from Miller, Flamm, and Milburn, and Rausendorf and Brigel showed that if the future measurements are dependent on the earlier measurement results and on the kind of measurement you do, you can get a deterministic computer, which was quite a surprise, I would say. It is very, very interesting. Here's a picture of a 4-qubit one-way quantum computer, which we did a few years ago. Here are the 4 qubits in this entangled state here, this cluster state, and you have feed forward in the sense that you, depending on measurement results, say here, you rotate the polarization here, you do a flip around X or Z direction for this state, and so on and so on. Here's a picture of the system which we have across the street here, and here's a list of some of the quantum computation experiments done with this, but I don't want to go into details. I want to come back and conclude my talk about the basic point. One of my favorite quotes is by Rabi, 1985. There was a Niels Bohr centennial conference to the 100th birthday of Niels Bohr, and there he said, I think we are missing a very basic point. The next generation, when they have found it, will knock on their heads and say, how can they have missed that? Now, this was said in 85, so the next generation is already in business, and they should do their job. Now, coming back to the discussion, which has to the basic point of my talk, I want to stress again, all this came only about because people were curious about entanglement and about fundamental notions in quantum mechanics. Now, the first experiment was certainly done out of philosophical curiosity. Nobody had an idea that this might be useful in a quantum information procedure. And I tell our politicians, and I also told them in the connection of the AC, that if they want us to do something useful, in the sense of immediately useful, they should not force us to do something useful. Because the long-range things are those where you cannot know when you work on it whether it might be useful or not. There's a famous quote by Faraday. He supposedly showed Sir Gladstone, who was the Chancellor of the Exchequer, which is the finance minister. At some time later, he became Prime Minister. He visited Faraday's lab. Obviously, Faraday was already sufficiently famous. And he asked them, this is all very nice, but what is it good for? And Faraday gave him the classic, I think many of you know it, the best answer you can give a finance minister. He said, someday, Your Honor, you will tax it. This was absolutely correct. To come back to Schrödinger, in my last quote, here is a nice quote by Schrödinger, which I like, from 1952. He said, in the first place, it is fair to state that we are not experimenting with single particles any more than we can raise ichthyosauria in the zoo. Well, the rest is we are scrutinizing records of events long after they happened, and so on and so on. Well, in that case, I think Schrödinger would be fascinated to see that the development in both cases went beyond his expectations. We are experimenting with single particles in the experiment, and I understand that our biology friends are not very far from raising ichthyosauria in the zoo. Thank you very much.